one such RF, there can only be one such RF. And the difficult part here is to show that it actually exists. Okay. Now, it might happen, and actually, so in the example that we're interested in, what's going to happen is that you're going to first fix this small parameter epsilon, and then at fixed epsilon, you're going to try to describe the solution as an element in one of these D-gamma spaces, and the whole point is that you want to have estimates that are uniform in epsilon. The conversion IPSSM goes to 0. So now for fixed epsilon, even though some of our things have negative degree and so on, and we in principle are not allowed them to be distributions, they will actually be continuous functions. Okay, so at fixed epsilon, our pi x's will actually be continuous functions. And if it so happens that they are continuous functions, then, well, it's actually quite easy to convince yourself that Rf of x has no choice. It has to be pi xf of x evaluated at x, which you can evaluate it. Okay, so, except that this definition here, of course, doesn't make sense in general, right? Because pi xf of x is in general a distribution, so you cannot evaluate it as x. Okay, but what the theorem says is that somehow if gamma is positive, in a way it actually does make sense. Okay. So, now if you do this, it turns out that these D-gamma spaces, you can actually recover many of the nice properties of, the usual properties that you sort of used to from other spaces. You could even model, so here I have a definition of D-gamma, you could imagine cooking up Sobolev spaces and so on, right? But stick to Hölder spaces for the moment. So you have usual kind of results. So for example, now multiplication. So if you want to be able to multiply things, you have to give yourself a multiplication rule on T. So in the definitions I gave so far, there was no, T was just a vector space. It didn't have any kind of algebraic structure on it. So if you want to be able to multiply it, you have to give yourself a product. So say you have a product on T. And there's two conditions that you want for product. The first one is that, the degree of a product should be the sum of the degrees. It's the natural property of products. And the second one, here, is to be a bit less obvious, should be that every element in this, group of operations, G, which do this re-expansion around a different point, should have the property that if you apply it to a product, it's the same as applying it to the individual factors and then multiplying. And this is very natural if you think of polynomials, because it really just says, you have a polynomial based at a point, and then you re-expand it around a different point, then that's the same. You have two polynomials based at a point, you multiply them, then you re-expand around a different point. So it's just the same as first re-expanding them around that point and then multiplying them. It's obviously the same operation. And so this is something that you would want to impose, which is extremely natural, just because of what I just said. And if you do that, then it turns out that, well, if you have an F1 in this D gamma 1, and you have an F2 in D gamma 2, and you multiply them, then it's again in one of these D gamma spaces, and it's actually not in general in gamma equals to the bit. Normally, for the usual Hölder functions, you end up picking the less regular of the two. So here in general, you actually pick up something even slightly less regular. So what you have to do is you have to look at what's the thing of lowest degree that appears in the description of each of these FIs. Okay? And then you look at gamma 1 plus the thing of lowest degree appearing in the description of F2, minimum gamma 2 plus the thing of lowest degree appearing in the description of F1. Okay, which is again sort of, it's not surprising at all actually, because it just says that, multiplying with something of negative degree is a little bit like taking some kind of fractional derivative, so you lose regularity in general. Okay, but you lose exactly the amount of regularity, which is sort of the lowest regularity appearing in the description of these guys. And then the other thing you want is a Schauber estimate. Okay, so because you want to take your equation and rewrite it as a fixed point problem, so you want to write it as an integral equation. And then it means that you want some kind of regularity estimate for convolution with the heat kernel. And you have exactly that. So it turns out that for this you have to somehow make more assumptions. So you have to build. The thing is that you need then for every element in your vector space T, you need some kind of linear map called curly I, which somehow represents the convolution of that element with the heat kernel in some sense. And then it turns out that you can actually build, so if you have this, so you need certain algebraic structure on the space T, and then you actually need also certain compatibility condition on this model, the sort of pi x's and the gamma xy's. Okay, so there's essentially a formula that tells you how the pi x should act on these elements here, given that you know how it acts on the tau itself. But assuming that you have that, then the theorem is that you can actually build a linear operator that improves regularity by 2, so it must d gamma into d gamma plus 2, and which has the property that it really represents convolution with the heat kernel in the sense that if you take a guy in d gamma, you add with this operator, and then you apply this reconstruction operator, so you look at the actual distribution that it represents, or function. Okay? Then that's exactly the same as first looking at which distribution it represents, and then just convolving that with the heat kernel. Okay? So you have this identity here, and furthermore that operator is actually of the form simply applying that linear map pointwise plus other stuff, and the other stuff is complicated, but the only thing one needs to know for the purpose of this lecture is that the other stuff is going to only involve elements that are proportional to the usual Taylor monomials. Okay, so in this part you actually need to have the usual Taylor monomials floating around. So you need to have the purple 1, purple x, purple x square, etc. if you want. So you have these, so let's assume that we have these two ingredients. Okay, so we know how to multiply things, and the amount of regularity you lose by multiplying is essentially the degree of the thing of lowest degree that appears in the description. And you have some Schauder estimate that allows you to gain 2 degrees of regularity. Okay, so here is what we want to do now. Okay, so for that 5-4 equations then. So first, you want to build one of these regularity structures which is sufficiently rich that it allows you to somehow encode all the operations that you need to turn that into a fixed point problem. Right? So using variation of constants formula, you would want to rewrite this. Right? So this equation you would want to, so the equation, remember, is dt phi equals Laplacian phi, and then say minus phi cubed plus the noise, and I would want to write it as phi is equal to the heat kernel convolved. So this is space-time convolution with sort of indicator function for positive times this right-hand side minus phi cubed plus phi plus just the heat kernel applied to the initial condition. Okay, so this is variation of constants formula. And so you see, in order to make sense of this equation, this guy, even if the initial condition is very irregular, the heat kernel is smoothing. So this is immediately a smooth function. So if I have the usual Taylor monomials, I can describe this guy to arbitrary order. This becomes a C-infinity function immediately. And then I need to somehow be able to describe this. And so you see, I need exactly the 2 operations that I just mentioned. I need to be able to multiply phi with itself twice, and I need to be able to convolve with the heat kernel. Okay, and here, well, I need to be able to multiply by indicator function with positive times. So this, I just multiply with indicator function with positive times. And so you want to build a structure which has sort of enough structure so that these 2 operations, multiplication and convolution with the heat kernel, make sense. And then you want to rewrite reformulate the equation of the fixed point problem in one of these d gamma spaces. And then you want to show that, well, that fixed point problem has nice local solutions, so you have usual kind of PDE theory for it. And furthermore, that solution would depend continuously not just on the initial condition, but actually also on the choice of this model pi and gamma. Okay, because now all this construction depends on the choice of pi and gamma. And so it depends on the model, but you want that the solution is continuous as a function of the model. And furthermore, you would want, now for every smooth noise, you want to be able to build a model in a kind of canonical way, so that if you feed this into this fixed point problem in d gamma and then apply this reconstruction operator to the solution, well, you simply get the solution to the original equation. And then you would want to tweak the definition of how you build this model from the noise in such a way that you actually make it converge to a limit. So remember, that was this randomization group acting on the space of models. And then you want to identify what did this actually do to my equation in order to see which sequence of equations do you have to look at in order to actually get a non-trivial limit. Okay, so that's the plan for the next 5 minutes. So one crucial remark here is that even though at fixed epsilon, in principle, all these objects are nice and smooth. So the usual product makes perfect sense, right? But nothing here forces anything like reconstruction of a product being the product of the reconstructions. Okay? So that's the crucial thing here. Right? Is that if you have a product up there, it needs to have certain natural properties and so on, but these properties don't actually determine it uniquely. Okay? And so even when everything is smooth, it's not necessarily the case that, if you have two guys f and g, each of them actually represents a smooth function, but you multiply them up there and then you apply this reconstruction to it. There's no reason why this should be the same as actually multiplying as the usual product of functions. Okay, that's not enforced here. And that's the whole point somehow. Right? Because that's how you could have suddenly additional terms popping out of nowhere in your equation. Okay, so now here's, so you rewrite the equation. Well, so this is what I just did on the blackboard, right? So the equation in the integral form is that. And now assuming that everything makes sense, I rewrite it as a fixed point problem in this d gamma space using this operator curly k, which came with that child estimate. Okay, so that's the one which is supposed to represent convolution with the income. And so what I've done here, you see I've just introduced a new symbol, purple psi, which represents the noise. Okay, so what I'm going to do is I'm going to postulate that purple psi has degree minus 5 halves minus kappa, because this is exactly the regularity of white noise. Okay, so if you take white noise, you hit it with a approximate delta function like this, you look at the expectation of the square of the thing you get exactly epsilon to the minus 5, or lambda to the minus 5, but that was the expectation of the square, whereas the thing itself has order epsilon to the minus 5 half. Okay, so the degree here should naturally be minus 5 half in dimension 3. And then, so capital psi should represent the noise. So what it means is that I would want this pi x applied to capital psi to be simply psi, or say psi epsilon. Okay, in particular, this doesn't depend on x. Okay, so this is a functional. This is itself a functional distribution, right? So this depends on y, and then this is the noise at y, but it doesn't depend on that point x. And so that means that I would want the gamma to act trivially on it. Okay? And so now, okay, so I can do that, but now you see, you note that if I do this, then somehow what I mentioned a couple slides earlier would force me to introduce lots of new symbols, because if I have that symbol psi appearing here, then this guy involves some map I of whatever. That means that I will also need that symbol. I need to have something which is the result of I applied to psi, and so what I do, I simply introduce a new symbol which I call I of psi. Okay? So I need a symbol I of psi, but now if you have an I of psi appearing in the description of psi, that means that now here I will have a I of psi cubed, and maybe also an I of psi itself, because in the description of psi I will have the purple 1, which should not change anything, and I will also need an I of psi square, etc. So you start to have lots of new symbols popping up, and all of them have natural degrees, because you know that the degree of a product is sum of the degrees, and the degree of I of